to thank everyone for being here and to say good morning, good afternoon, or good evening, depending on where you are at the moment. And thank especially Paulo and John for making all of this possible and to kindly invite me to show some of my work. So the thing is, I'm saying some of my work, which is a bit selfish. It's actually a collaboration with Stéphane Perard and Mathieu Labousse, both in Paris. And all of this took place when I was still a very young PhD student, still trying to learn what all of this was all about, and which has also been kindly and nicely supervised by Nicolas van der Waal from Belgium, which was my PhD thesis advisor. And of course, want to thank the funding agencies, the ARC Coendrops back in Belgium, and also the CC for computational resources. So the thing here, there's been so much said on quantum mechanics. And I mean, obviously, there is so much to say on the system from that aspect with absolutely incredible dynamics and analogies. I have to say that I have a slightly different point of view here, which is basically the one of active matter and statistical physics. Because from that point of view, too, the system is absolutely stunning. What you have here is a system which basically is able to change its behavior with one parameter that you cannot find anywhere else. So at least I don't have example as precise as the one of working droplets. And this parameter is the memory of the system. And it is not some kind of, theoretical fantasy. This is really something that is happening. You really have the experimental setup, and you basically have a gear which is written acceleration and basically which relates to the memory with a completely unique mapping. So this is really a unique kind of trajectory. And when I say that you have an increasingly complex dynamics as you change this memory, you can basically go from simple, let's say, self-propulsion. And when I say simple, it's already so difficult. Well, I mean, whatever. But you have this self-propulsion here, and this video is taken from a previous article that we published with another PhD student in Belgium, where you have basically I would say the steady motion of a droplet above an underwater cavity. And basically here, what you have is some kind of balance between the dissipation of the motion due to the interaction with the air in below the droplets, and the pumping of energy, which basically arises from the interaction with the wave field that the droplets generate. And as you keep increasing this memory, things get even more complex. Here is a nice example from Stéphane Perard experiment back in 2014, where he basically put a drop in the harmonic potential. And what you see here in the movie is that you have a circle that degenerates into a lemniscate. And what you're seeing here is basically the trajectory that adapts and basically self-organize so that you minimize somehow the wave field according to those trajectories. So we already have a self-organization of waves on the interface, which, as you might know, leads to quantification of macroscopic observable angular momentum and mean extension in this case. And finally, and this would be basically where we place ourselves in the high memory regime. I mean, John was saying this yesterday. I mean, this is basically where all the fun is happening. And here, for illustration, I took this nice video from the experiment of Dan Harris in circular cavity, where basically what you have is a droplet which is navigating in a very complex landscape that is self-generated by its successive bounces on the interface. And so basically what you have here is a bouncing droplet, a self-propelled object, which is interacting with its own path, which creates somehow this very, very complex landscape. And so while investigating that, once again, as a young PhD student, I remember Stéphane Perard, which used to ask me the same question again and again and again. And I hope I finally found an answer, and I'm going to share it with you, which is basically in the high memory limit. Well, as I say, you have self-propelled particle in a chaotic landscape. And so the question is how different it is from an active Brownian particle. And when you see all of that, well, the question is not as simple. And there is another question, which is closely related to this one, which basically asks the question of what in a dynamical system, how things will change as you basically increase and increase and increase the amount of information that you place in that system. And so those two questions are obviously very connected. And they are also, quite antagonistic somehow. And I will keep this little teaser for the conclusion of the talk, try to explain to you where this somehow paradox that I'm teasing arises. So let's try to answer those two questions. And to do so, we basically published the first article and submitted a new one. So that's basically a two-part story here. The first part has been in free space, where we investigated the run-and-table dynamics of Walker in free space. And if you're interested in that and you want to have a deeper insight into those dynamics, I invite you to go in the article. It's a PRE in 2019. And what I'm going to talk to you about today is basically the dynamic of Walker in harmonic potential in the limit of very, very high memory. And we're going to do that from two points of view, which is experimental, a bit of experiment and a huge load of simulations. So let's try to set things up nicely. So what I'm showing you here on the left side of this of the screen is basically trajectories that you obtain from experiment and simulation. So the experiment are basically the one from Stéphane Perard, where you have a droplet which is bouncing on an interface. I mean, as usually with your walker, but the core of this droplet is made of ferrofluid. And thanks to that, basically, by placing these droplets in an external magnetic field, in a spatially varying magnetic field, what you can have is the gradient of that field will apply a central force, confine the walker in a given area of space, and basically place it in an harmonic potential. And so the kind of trajectory you can observe are reported on the top left. And to compare that, to have a point of comparison with the simulation here, I'm basically taking the algorithm developed by Emmanuel Faure, quite a long time ago now, which is basically an event-driven algorithm. So you basically solve a discrete version of the dynamics. And these dynamics takes into account the two main effects or two main properties of the dynamics, which is the bouncing dynamic of the drop and also the interaction with the wave field. So you basically have a summary of what the algorithm is basically solving, which tells you that the velocity is related to the previous velocity, some interaction with external forces, a coupling to the wave field, and some higher order terms that are taken into account in simulations. And you also have, of course, the wave field that is being taken into account, which is written on the lower part of the screen. And so there is a few things that I want to discuss here, just to make things clear for everyone. So the harmonic potential you are going to use for that talk are actually pretty soft. So the area basically is quite, for the walker, is quite large. And that's basically to be sure that we capture the effect of the wave. And that's going to be one of the main focus of that talk. And that we haven't confined too much the walker into such a way that basically the investigation here. And every value of the memory that I'm going to give you are also expressed as, I mean, a few years ago, that's what we used to call the French notation. I don't know if it's still referred to like this, but it basically measured the number of impacts on the surface, which are still emitting waves, and those waves are still affecting the dynamics. As you can see here from the two examples, you have memories which are of the order of 250 or 200, which is basically what we could reach, one of the maximum value that we could reach experiment. And as you can see, well, you have this, I mean, next to the trajectory, the PDFs for the position of the walker, which show a very nice, I mean, you can guess some kind of Gaussian profile, which is going to be the focus, one of the two focus of that presentation. So the walker, I mean, obviously is not only a particle, it's also waves, which is a very, very important part of the dynamics. So there is basically two systems you need to investigate: the wave and the object. And well, you have to make a choice on which one you're going to start with. And I basically suggest that we start with the waves. So the thing is, the value of the memory that we're going to go for can reach value up to 25,000, which basically means that if you want to make computation of the information stored in the wave field, you basically have to deal with a ginormous amount of information, which is not very computationally effective. And so if at some point you want to, let's say, investigate the properties of the wave field, let's not bring it like this. So if you consider the formula that I gave you before, well, the wave field is basically expressed relative to the position of the walker, which is not so interesting here, because as I say, it makes things complex, and you need to take into account all of the previous bounces of the drop to simply access the energy and so on. So one of the nice way to simplify the analysis of the wave field is basically to say, okay, what about instead of referring everything with respect to the walker, I'm doing that with respect to the center of the potential that I'm applying. And so doing so, you have this very, very cute and small expression here, which basically express everything as eigenmodes of the waves centered on the potential. And those eigenmodes are illustrated in column B that you can see on the right side of your screen. And with all of those eigenmodes that are basically the basis of the composition for the wave field, you have amplitude, which are the AP in that case, which are complex quantities, and for which you have an illustration here coming from simulation. You see this is a quite complex and chaotic-like system, I mean, time series. But basically, now you reduce this very, very large amount of bounces to a collection of mode fields. So that's basically of eigenmodes, sorry. And so that's basically a quite efficient simplification of the problem. And also, and I mean, it may bring a few discussion, but let's keep that under the rug for the moment. But you also can define an energy for the wave field, which is a very, very nice expression. It's basically the sum of all modules squared of all wave field in the available to the whole curve. So we really have a very insightful definition of the energy. So as I say, all of this is pretty chaotic-like. So what we need to do is basically to take the statistical point of view on this problem. And so what I'm showing here to you is basically the probability distribution function of the AN square in semi-logarithm scale. You have the graph on the left side of the screen. And what you can see here is basically straight lines, which basically says that the distribution of the AN is something that follows a Gaussian distribution. Another thing that you can realize is also that you have a curve which seems to somehow, not fit with all the other. And this one is basically the mode n equals 0. So if I go back slightly and you look at the first row of illustration, this is basically the axisymmetric mode. And since this one shares the symmetry of the potential and the trajectory, we expect this, this mode to be slightly different than the other one, to behave slightly differently. And on the other hand, what you have for on this graph, you have n equal to 1 up to n equal to 7. You basically have, once again, a Gaussian distribution, a straight line in that graph. All the curves seems to kind of merge with each other and are not very easy to distinguish. So to be sure at some point that we can understand what's going on, and to quantify this a bit further, what we decided to do is to take for all of these values of n from 0, and in this case up to 125, the root mean square value that you have for the corresponding statistics. And that's basically what I'm plotting on the central part of the screen. And I'm also showing that for different value of the memory. And for you to maybe have a bit more insight of the kind of, variation of memory that we consider, the whole curve here, the three curves, are basically spanning from 500 in memory up to 10,000. So you have a 20 times increase in the value of memory. And you can see that the values are not changing that much. You barely have an increase of a factor of 2 that are root mean square values for the amplitude of the eigenmodes. So that's a rather low increase for 20 times more bounces considered. But something that is interesting is that you basically start to stretch that profile to larger value, which basically tells you that you start to activate more and more modes, which we're going to discuss in a few instants. And finally, what you have is the probability distribution function for the energy of the wave field. And basically what you have there are gamma-like distribution. That's basically what this solid line is showing you, which is not something that is so, so weird in the sense that you're basically summing Gaussian random variable, and this is the kind of distribution you might expect from that. So not so weird here. Okay, so let's keep that aside for just 2 seconds. So we know we have that. We can also check it from the experimental part. I mean, I'm sorry, I didn't make it clear, but these were simulation results. But here, what I'm showing you on that slide are experimental results, and that basically tells you that you have the same kind of behavior. So it's a bit more, there is more fluctuation because there's not that much statistics, but you'd still have the AN distributed according to Gaussian distribution. You still have this bell-like curve for the root mean square value as a function of the index of the mode available, and this gamma-like distribution for the energy stored in the wave field, which basically says that, well, the simulation are definitely showing the same kind of statistical behavior as the experiment, and we are quite happy about that. Okay, so as I say, so we have all of those results and we have all of those statistics, and I remember back then when I first investigated all of that, I was really wondering, what can you say about all of this? I mean, obviously, this is you have tons and tons of information, but how to make sense out of them? And one of the ideas was the following. We have the trajectory of the wave. That's what I'm showing you here with a typical result from the simulation, and you have the corresponding PDF for the position. But this PDF is not only the PDF of the position, this is also the PDF of all the position of all the active sources of waves. And so what you can do are 2 things. Out of this very distribution, you can basically say, okay, I take a segment, you cut basically a part of the trajectory, compute the wave field out of that. This is part of the real trajectory of the walker, and you will have the real, let's say, information about the wave field. That's what we did before. That's exactly the graph that I already showed you. But what you can do is, okay, what about I take the exact same amount of position of impact that I randomly draw out of this distribution? And so basically you will have the same underlying statistics for the generating particle. So in that case, the walker, you will have the same generating statistics But what's going to happen here is that you basically break all of the time correlation that you have in the system. And so that's a very nice way to see at some point what the Walker is all about. So doing so, we bring back the same kind of graph and you see what are difference. There's the same graph as before. On top the Walker, bottom the randomly generated field. And what you see here is that basically the distribution of the AN squared is still an exponential. So basically the AN are still distributed according to Gaussian distribution. You can see that the x-axis is different despite being at the same value of the memory and frequency of the external field. So this is something which is already quite funny. If you look now at the evolution of a root mean square value of the AN as a function of n, one of the striking aspects of that is you are not, you see that you're really blowing up in terms of amplitude. You see that there is a significant increase of the energy stored in each mode. But on the contrary, you don't seem to really push that curve to larger values of n, which really seems to say that you are not really activating new kind of eigenmodes in the dynamics. And that's something that we're going to discuss on the next slide. And last but not least, the energy. Well, once again, you have this gamma-like distribution. The solid line that you have on the random part is once again showing a gamma-like distribution, sorry, which is fitting the curve. But what seems also to appear is that for the same value of the memory, you don't have the same increase in the average energy of the work, which is something that we're going to discuss right now. So let's try, as I say, to discuss these root mean square values of A and this energy evolution as a function of the memory. So the first thing that we do is to try to define the number of degree of freedom which is activated by the wave field. And so to do that, if I briefly go back to the previous slide, it's basically saying that you approximate this bell-like curve to a box with the same area under the curve. That's basically what you say. So that's a way of measuring the amount of modes which are actively participating in the creation of the wave field. And what you see in this DOF, which is the number of degree of freedom as a function of the memory in logarithmic scale along the x-axis, is that you definitely increase the number of degree of freedom in the Walker case with this field symbol, while the random situation with the open symbol is basically staying at a value of 20 for that particular realization. And the reason why and how you can understand that basically comes from the, as I said, the correlation with the Walker dynamics. If you now go back to the trajectory of the Walker, what you see is that sometimes you really make this gigantic loop in the in region of high energy. And doing so, what's happening is you start to basically inject energy into high indexed mode. If you look at the illustration of the eigenmodes that you have, you see that basically when you're close to the center, you activate low index mode like p equals 0, but the high order mode like p equals 20 are flat at the origin, which means that something bouncing there is not activating that. You really need to go out to really do these kind of things. And so the fact that you have those loops away, which are a feature of the working dynamics, really gives you the possibility to pump energy into the mode of high amplitude. And the more important the memory is, the longer it will stay there because you get trapped and so on. And then you start to activate different, more, eigenmodes with higher index in the dynamics. And this is not done by the random case because you basically have a random and I would say homogeneous distribution of wave sources because you draw it from the random, a Gaussian distribution, but you don't correlate, you don't activate in a significant and statistically relevant way other types of modes with a high index in that case. So that's something which is quite nice because you can really control through the memory basically the dimension of the thermostat that is basically being built by the waves. Another very interesting feature, and I realize that I'm already some time. So another interesting feature is how the energy is evolving as a function of the memory. And that's basically shown on the left bottom part of your screen in double log scale here. And once again, field symbol is Walker, open is random. And the Walker really show a smaller increase of the energy with the memory. And that's not so weird because it's kind of correlates to previous researches done by Stéphane Perard actually, and Mathieu, of course, where basically the Walker seems to favor destructive interferences and somehow mimic some kind of minimization process within the wave dynamics. So that's really nice at that point that the correlation that you have in the dynamics, the correlation between the different impacts due to the Walker are basically doing two things, giving you a control on the number of degree of freedom that are stored into the wave field, but also basically favor destructive interferences to mimic some kind of minimization process, let's say, when it comes to the energy stored in the wave field. So that was for the wave field point of view. Now let's a bit go back to the particle, because I mean, I still have this question of active random particle. So if we do that, well, let's take the simplest example, I mean, the simplest way of investigating the dynamics, which is basically looking at the forces applied on the walker originating from the weight. And just for the sake of simplicity, we make the we only take the x component of this force. It will be the same thing for the y component of the force, simply because you have an axisymmetric dynamics. So it is. And so what you see here is for 3 different memories, where you have a 50 time increase in the memory coming from violet to orange, is that first, you really seem to lose correlation. And second is you don't seem to have a significant buildup of the amplitude of that force. So you are increasing memory 50 times, but you barely see a change in the fluctuation of the forces. That's already quite interesting. So let's start digging out this story about the correlation. So what you have on this B panel of the slide is the correlation of the force along the x-axis. Colors are the same as in the previous figure. And what you see is that basically, as you increase the memory, as you change colors, you basically lose the correlation along the x-axis. You have nothing, and basically everything comes to 0 when it comes to correlation, besides just a small bump at very, very short time scale, something that we can discuss if you're interested in that. But something that is interesting is, wait, there is still some self-propulsion somewhere. You cannot simply say that there is no correlation anymore. And so we simply checked what's happening in the tangential direction of the motion. And using, the non-normalized correlation function, you really see here the self-propulsion arising, because the flat lines that you observe are basically on the self-propulsion. Indicates you the self-propulsion. Those flat lines are not at 0 and indicates you of the self-propulsion that you have in the dynamics. And once again, the correlation disappears as you increase the memory. So that's quite interesting, because I can already bring it now. You're increasing the amount of information. You're basically putting time correlation by putting more memory. And yet the walker is basically getting more and more amnesic. So this is already quite fun. Another thing that I want to discuss are the distribution of those forces, once again, for the 3 value of the memory that I'm showing to you. And this is in semi-logarithmic scale. So what you have is a Gaussian curve, and basically telling you that with a parabola, which is indicating a Gaussian curve and a Gaussian distribution. And what is quite interesting, and goes back to an observation I already made before, you barely change the shape of that curve. You increase the memory 50 times, and you basically have no change in the standard deviation, in the width, let's say, of that distribution. And last but not least, we wanted to have a quick look at the power spectrum here in double log scale. And so you have the 3 curve for the 3 scales that I'm discussing from the beginning of that slide, but you also have a solid curve, which is basically what you would expect at very low at very low memory to give you a point of reference. And what you see is, as you increase the memory, the memory of the trajectory, so this peak that you have around 10 to the -3 period -1, basically disappear, and you have a completely flat signal over 3 decades of frequency. And you just have then a sharp decrease, which basically corresponds to a high frequency. This is what you would expect for the self-propulsion. And so what is really striking at that point is, what I'm telling you is, I'm putting more and more information, I'm correlating more and more the dynamics, and how it shows up is basically by giving you a perfectly well-defined white noise with a self-propulsive force. And that's something which is absolutely stunning, because once you have that, you're like, okay, so there is theories for this kind of stuff. You just have to dig into any kind of literature you want. And if you do that, you can find an easy function, for example, for the probability distribution function for the position of the walker and for its speed. And what I'm showing here in panel A and B are basically the distribution function for the walker for a collection of different frequency in a given memory. And you see here that rescaling everything by the energy of the walker brings all of the curve on the same line. And you have this fit also on the solid line is basically the theory in what you would expect. It's working absolutely perfectly with only one fitting parameter, which would be the equivalent of this effective temperature that I'm going to discuss in a few instants. But I've also placed with the black symbol on the graph, the experiments also. And you see that the experiments are also quite fitting well on that one. Once again, fluctuation, but lack of statistic. But still, I think this is rather convincing. And then you can do that for the speed. So this is now a self-propelled system. So you see there is a maximum around a kinetic energy of 1. Everything is plotted as v squared divided by 2. And you see that once again, all of the curve superimposed to each other perfectly nicely here for all the different frequencies. And this is also very convincing when you compare to that the experimental data. And all of this is basically theory of active Ronan particles. And last but not least, and that basically goes back to the shape of the distribution for the forces applied to the Walker. When you look at beta minus 1, which would be the equivalent, let's say, thermal energy of the Walker, what you have is something which is barely evolving. As you can see on the y-axis of that graph, panel C, you're basically switching from a value of 1 to a value of 10. This is absolutely nothing. While you are basically spanning 3 decades of values of memory parameter along the x-axis. And basically, and I don't know if you can see it here because I had the zoom panel on the bottom of the screen, but basically the power law, because you can fit power laws to that thing, is basically with an exponent which is smaller than 0.1. So you can basically say that the thermal energy is almost, how to say, independent of the memory. And that really brings one thing that's actually quite like here. If you only look at the Walker, you will basically not be able to say if the memory is big or small in this regime. You really need to go in to dig into the wave dynamics to basically be able to access missing information about the problem. So that was a long talk, and I'm sorry because I realize I'm already 5 minutes above my due time, so I apologize for that. But basically, what kind of answer can we bring to the two questions I've been asking you at the beginning? How different a Walker is from active Ronan particle? Well, my answer is it's not. And I hope I've been convincing enough. I mean, basically, it's submitted to a completely, perfectly well-defined white noise. But what is interesting is if you now take a second question, what is the consequences of an increasing amount of information in memory-driven dynamics? You take a non-Markovian process, because this is what the walking droplet dynamics is all about. This is a non-Markovian dynamics, but by overloading the memory, as we go back to the title of that, by overloading the memory, what you're basically doing is switching this non-Markovian dynamics to the Markovian realm. And that's absolutely stunning. And all the time correlation that you're missing in the particle dynamics are all in the wave. And so the Wavefield is really the part of the dynamic that you need to watch for, because if you only look at the particle dynamics, you don't see anything. So I thank you for your attention. I mean, it has been a pleasure to share all of this with you. And I want to finish on maybe one little token of wisdom coming from the walking droplet experiment. Basically, one of the conclusions that you can draw out of all of this is saying that if you want to go far, if you want to keep going ballistic, don't get dragged behind by the amount of souvenirs that you might have. And I think this is a very, as I say, nice token of wisdom that comes from the walking droplet dynamics. Thank you very much for your attention.